Welcome back. We'll be looking at another example of multiple component material balances. In this particular example, we will be seeing another way of using process specs, and we'll also see one with math that is a bit more complicated. So, let me find the example. There it is. Okay. A countercurrent extraction process is shown below. The feed in this case contains 0.1 kilograms of xylene per kilogram and 0.9 kilograms of solids per kilogram at a total flow rate of 1,500 kilograms per hour. In the drawing, I've marked that as stream 1. The extraction solvent, which I've marked as stream 4, is pure benzene at 750 kilograms per hour. The mass fraction of xylene exiting each unit in the extract stream contains no solids and is 10 times that of what's in the solid stream. Okay, so that's a little confusing, but this is going to be our process spec, and we want to know what percentage of the xylene is recovered. So we're going to be looking for how much xylene is in stream 6 compared to how much is in stream 1. In this particular case, the process spec here says the mass fraction of xylene exiting each unit in the extract stream, so that's going to be in this stream or this stream, depending on which extractor, will be 10 times greater than that in the solid stream. The solid streams will be these. Okay. So let's see how we can put these together to solve a problem. So we are given that the feed contains 90% solids and 10% xylene with no benzene. That flows at 1,500 kilograms per hour. We are told that the solvent, stream 4, is pure benzene at 750 kilograms per hour. We are making the assumption that the benzene never leaves this chain of streams and that the solids never leaves this chain of streams. Now that is an assumption that we are having to make. So those are, I'll just put a little star on each of those. These are assumed values. When you get into some future courses and you learn a little bit more about how extraction works, you'll see that those are reasonable assumptions. For now, they just simply are going to be necessary to solve the problem. Okay, so the rest of the things, I don't really know what they are. Since we're focusing on xylene, I'm going to call this X2, X3, X5, and X6. This therefore would be 1 minus X5. They have to add up to 1. 1 minus X6, 1 minus X2, 1 minus X3. The flow rates I'll just call F2, F3, F5, and F6. So let's move on. Next, let's look at the degree of freedom table. Now, we have two different pieces of equipment, the extractor 1 and extractor 2, and of course we have the overall system. So let's look at each of the extractors. So extractor 1, stream 1 and 5 comes in, streams 2 and 6 leave. The variables associated with those streams, well, stream 5 has X5 and F5. Stream 2 has X2 and F2. And stream 6 has X6 and F6. So we have a total of 6 unknowns. How many material balances can we write? Well, we have 1, 2, 3 components, so we can write 3 material balances. Sum of x's, well, because of the way I set these up with using x2 and 1 minus x2 instead of like x2 and y2, I get 0 sum of x equations. I've already used those to define my equations, my variables up ahead. Now how about process specs? Well, the process spec was that somewhat confusing expression that we had about 10 times the xylene is recovered. Okay, so I have one for each extractor. So there is a process spec. Now, that process spec in this particular case says that the amount that leaves X6, F6 is equal to 10 times the amount, well, the amount that leaves in one stream is 10 times the amount that leaves in the other stream. Okay, so this is the process spec for extractor 1. Now the degrees of freedom in this case are going to be 2, so it is not adequately defined for me to solve this directly. So let's look at extractor 2. Here I have streams 2 and 4 that come in, and streams 3 and 5 leave. In this case, the variables are x2, f2, x3, f3, and x5, f5, which is 6 variables. We're going to see that this is very much the same. I have 3 components, so 3 material balances. I have no sum of x equations, and I have one process spec. This time the process spec is that x5, f5 will be 10 times x3, f3. My degrees of freedom is, of course, 2 again. Still not well defined. What about the overall system? Well, overall, I have streams 1 and 4 that come in, and I have streams 3 and 6 that come out. So my variables in this particular case, stream 1 is well defined and stream 4 is well defined, but streams 3 and 6 are not. So I have 4 variables. In this case, I have 3 material balances. I again have no sum of x's because I used those in defining my composition breakdown. But I also do not get any process specs. Now, this is the part that confuses people frequently. So x3 and x6 are both unknown. And so x6 is involved in this one, x3 is involved in this one, but each of these equations involves variables that are not in my existing list. So I have no process specs that specifically apply here. So I still have 1 degree of freedom, and therefore none of my variables, or none of my processes rather, are well defined for solving the system directly. So when you don't have one of them that is well defined, then the best thing to do is to just start writing down what these equations are. So I see that I'm going to be able to write a total of 9 independent material balances plus my 2 process specs. Let's just begin writing these down. So for each piece of equipment or the overall process, I can write down a total balance. Those are usually the easy ones. I can write down a xylene balance. Those are useful because they relate my process specs. But then I also have solids and benzene. So these are the material balances that I'll be able to write. For extractor 1, let's see if I can write extractor 1. These balances, looking at what comes in and out, Okay, so those are my balances on extractor 1. I can do a similar thing for extractor 2. And finally, for the overall process. Okay, so those are my material balances. And again, we have those process specs. I'll just write them here for sake of completeness. Okay, so this is the complete set of equations. Remember, I've got more written here than are actually independent, but this is kind of what we need to work with. So now then, how do we approach actually solving these? Well, my best advice to you is that I promise you the process specs have to be used. So I usually start with those and seeing how I can use those other places. And in this particular case, they are all about the quantity of xylene. So that means that I'm going to want to use these xylene equations heavily. So I'm going to insert these into the xylene equations. If I look at the, just kind of doesn't matter, but extractor 2, xylene equation. Okay, in that case, that says that x2, f2 is equal to x3, f3 plus x5, f5. But we have a process spec that says x5, f5 is 10 x3, f3. So x3, f3 plus 10 x3, f3. So in other words, x2, f2 is 11 x3, f3. Okay, that probably doesn't look that useful at this stage, right? But I also know that x6, f6 is 10 x2, f2, but x2, f2 is 11 x3, f3. So this is 110 x3, f3. And we had already stated with our process spec that x5, f5 equals 10 x3, f3. So I have all of these quantities of xylene in terms of one quantity, the amount that's coming out in this stream here. Okay, so let's see how that helps me. Well, we can go to any of these other balances here, but for instance, I know that if I do the overall xylene balance. Okay, that tells me that 150 equals X3F3 plus X6F6, which is 110 X3F3. So 111 X3F3, which tells me that X3F3 is going to be 150 over 111, 135 kilograms per hour. I can go through and find any of these others. Okay, so I now know how much xylene is in any of these streams. I could then use that information and manipulate variables to find some of the other quantities. But at this point, I actually am ready to answer the question, because remember that the question was, how much of the xylene is recovered? So how much xylene is in stream 6 compared to how much was in stream 1? And fortunately, I've got those numbers. 148.65 exited in stream 6, 150 entered in stream 1, and so therefore 99% of the xylene is recovered. This concludes this example. We will continue with doing many, many more examples. This requires practice. When you have had enough practice that you feel comfortable by working through problems in the textbook or looking at these videos or videos from other people, then you're ready to move on to the next unit.